SIS stands for safety instrumented system? No, SIS stands for Superman in the system. Yeah, I mean seriously. Like a Superman, the safety instrumented system is waiting when the system is completely normal. There is no action from SIS. But as soon as the system experiences an hazard, the safety instrumented system is going to come in between and stop the hazard and protect the system, protect the assets and the people. Now let's look at a real industrial example. So first is, imagine we'll take a level control loop, a simple level control loop. So basically, as the level is increasing or decreasing, this control valve is going to control the flow and basically control the level. Now imagine instead of water we have a dangerous fluid, and this fluid is increasing completely, and this wall which we see at the inlet fails. Now imagine this tank is going to blast, so we need something to protect it, right? If this dangerous liquid comes out, so we have a pressure system. So as soon as the pressure increases, this wall is going to open up and is going to release this extra liquid out to the sump. Now here if you see, there are two systems. The green one which you see is what is going to work in the normal cases. So this is called as your BPCS, basic process control system, and the red one which you see is what we were calling about the Superman in the system, also referred to as SIS, safety instrumented system. But let us look and divide these components together and find out in depth how does it work. The first thing is, safety instrument system is basically usually divided into individual SIF. They're called as safety instrumented function. So lot of safety instrumented functions come together and form a SIS, which is safety instrumented system. Now usually in the start you will have a sensor. Basically it is monitoring the parameters, and then it is given to the logic solver. Depending on the input, the action to be taken or not, that is given by the logic solver, and then an actuator or something which has to take action is present in the SIS loop because it is an active loop. Now in our example, if you see, I have another question. When the yellow valve failed, don't you think there is a chance that this valve which you see here can also fail? Then what if this valve fails and the liquid is still rising and the level is increasing to an extremely hazardous level and the tank might blast? What do we do in that case? For that case, engineers have a very interesting study called as PHA study. What does PHA stand for? It stands for Process Hazard Analysis. So engineers come together and decide how critical is the process and how much safety we require. So basically, let's get to our example. Now in our example, if you see, this individual loop will basically be used and understood that what if the tank fails, how much is going to be the hazard, and based on that something called as a SIL rating is given. This SIL rating basically is depending on how critical is the loop. So SIL is usually divided into SIL 1, 2, 3, 4, with SIL 1 being the lowest and SIL 4 being the highest. So depending on your application, a targeted SIL value is given as per the study. Now these individual components which we just now saw as called as SIF, safety instrumented function, have to meet that SIL. In order to meet that SIL, you have two criteria. The first one being is the quality of the thing. So basically each individual components also have a SIL rating. Now the higher the SIL rating, the lower is the probability of failure on demand, which is called as PFD in short. So the higher SIL 4 will have the least PFD, SIL 1 will have comparatively and higher PFD. So depending on how the SIL rating is required, we have the SIL rating for individual components. Then the SIL rating of the entire loop is calculated based on the individual SIL. So if you have a PT having SIL 3 but your control wall is not SIL 3, then your entire loop cannot be SIL 3. So now let's look at the next case. This is about redundancy. Now what happens is, you can't always have high quality materials to, and there is a limit to it, right? The next important thing is, what if we have redundancy to take care of this? So for example, what if this is a PT going to a pressure transmitter, or from here it's going to a control wall? What if one PT fails? What if two control wall fails? Still you will have a loop coming from a pressure transmitter logic solver and still an action will be taken. So this is what we call as redundancy. But imagine a case where two PTs are giving different signal. One is saying open the valve, the other is saying close the valve. Now what? Isn't this a big question to be answered? Let's look what happens at that position. For this, similar to how we have elections, it is exactly the same concept. So you have people voting. Let's imagine three people are voting. So there are three number put here. Then you have how many votes are required for the candidate to win. For example, in our case, if there are two votes given in favor of the candidate will win the election or the action will be taken. So basically this same concept is used in SIL, which is called as 2 out of 3, 1 out of 3. So for example, in our voting logic case, imagine when you have this, the first one will always stand for the number of devices that are going to be voting. So for example, if three pressure transmitters are voting, then the number will be 3, and the total number of votes required for the SIS to act. So for example, 3 devices are there, and if there are 2 votes in favor, the safety action will be taken. Now let's look at an industrial example. So imagine here's our line and 3 pressure transmitter are placed, and here's our logic solver and the final control element. Now in this system, these 3 PTs are put in the logic of, let's say, 2 out of 3. That means if 2 PTs are voting in terms of a safety action to be taken, then there are 2 votes in the favor of the action. So the safety action will be taken and the control valve will act accordingly. But imagine if there is only 1 PT which is giving the vote to open the valve. Even though the voting is given, still the control valve will not operate. Why? Because the safety action has to be taken by at least 2 votes. So this was not the action to be taken. After a lot of hard work and research of almost 5 years, looking at the most asked job interview questions, especially for instrumentation control engineers, finally there is a crash course available. And this crash course consists not only just of pressure transmitters, temperature instruments, level instruments, flow instruments, but it also includes control valves, relief valves, and on-off valves. Not just this, it also includes control system questions. And the best thing about the course is that this course is completely free of cost. And the best thing is, just when this course got released, there have been almost 305 students in just 3 days with an amazing rating of 4.8 out of 5 as of now. Come on, grab this course, take this interview questions, and trust me, this course is genuinely going to help you revise almost all of instrumentation. And let me know in the feedback section what else do you want. Let's make instrumentation an amazing branch. So till then, happy learning, take care, and let's meet in the course.